So if you're in a room of some kind, I encourage you to try a little experiment right now. So look around the room and see if there's something in the room that's made out of wood or maybe paper or cloth. And it's been in the room for some time, so hopefully it has the temperature of the room. And then find something else that's made out of metal that's also been sitting in the room for a while, and it doesn't have its own source of energy, so don't use your computer. It should just be something that's just been passively sitting in that room for a while. It's not too hard to find. And touch them both. And what you will see is even though they've both been sitting in that room for a while, the metal is going to feel a lot colder. The metal is going to feel colder. And this is a bit of a conundrum, because they've both been sitting in this room for a while, so they both should take on the ambient temperature. So let's make this a little bit more concrete. Let's say that the temperature of the room, let's say it's 70 degrees Fahrenheit. And the key for this feeling colder is that the ambient temperature of the room is less than your body temperature. Your body temperature is going to be roughly 98.6 degrees. 98.6 degrees Fahrenheit. So let me write this. This is body temperature. And the temperature at the surface of your skin might be a little bit different than this, but let's just assume that it's roughly 98.6 degrees Fahrenheit. And so what's happening is that this metal surface isn't actually colder. It doesn't actually have a lower average kinetic energy than the wood surface. If they've both been sitting in this room for a while, they're both going to have the ambient temperature of 70 degrees Fahrenheit. So what just happened? Why to your skin, to your brain, does the metal actually feel colder? And the simple answer is it's better at taking the heat away from you. So why is it better at taking the heat away from me? Well, let's just imagine, let's say that here are the atoms on the surface of my skin. So these are the atoms on the surface of my skin, on the bottom of my skin. Let's just say my hand is touching a surface like this. That's my thumb right over there, and I'm touching the surface. And it's going to have an average kinetic energy that would be in relation to a body temperature of 98.6 degrees Fahrenheit. So these things are going to bounce around or vibrate around. So they're going to have, and maybe the covalent bonds between the carbon molecules and the carbon atoms and the other atoms on my skin that keeps them from kind of breaking free fully, but they're going to be kind of oscillating around, bouncing around a little bit, and they'll even kind of push on each other, and this could be kind of the electrostatic forces doing it, but they're going to have some average kinetic energy. And let's say my hand is touching both of these surfaces at the same time. So I have the wood surface. Right, let me do this in a different color. So I have the wood surface. I'll do that in yellow. So I have the wood surface right over there. That is wood. And I have the metal surface. I'll do that in white. So I have the metal surface right over here. And this metal surface we already talked about is going to feel colder. Let me draw the rest of my hand actually. So the rest of the rest of my hand. So there you go, or my arm. So you get the idea. So what's going on here? So let's just think about it at a microscopic level. So the wood, first of all, its surface is going to be uneven. So you're going to have atoms up here, but then you're going to have gaps. There's going to be air here. And let me actually scroll down a little bit. So it's going to be like this. So you're going to have gaps like that. And it also has internal gaps. It'll also have internal gaps like that. So this would be the wood, while the metal is much denser. The metal is much denser, and the surface is actually much smoother. So the metal is, let me do the metal in that white color. So the metal, the atoms are much more closely packed. It is much denser. The surface is smoother. It won't have any internal air pockets. It's not going to have any internal air pockets in it. And so what's going to happen? Well, we've always said you're going to have a transfer of heat from the higher temperature system or the higher temperature thing to the lower temperature thing. And so they're already going to have some kinetic energy. So these things are going to have a kinetic energy that's consistent, or an average kinetic energy that's consistent with 70 degrees Fahrenheit. So let me just draw a couple of these arrows. Same thing over here. They're going to have the same average. They're going to have the same average kinetic energy. So these things are all jostling around, bouncing around, and pushing on each other with the electrostatic forces. So hopefully this gives you an idea of things. But my hand is warmer. My hand has a higher average kinetic energy, and so the atoms and the molecules in my hand are going to bounce into the atoms and molecules of the wood, and they're going to transfer the kinetic energy. But what we realize in the wood is I'm making less contact because the surface, first of all, the surface of the wood isn't smooth. So I'm making less contact. So this one right over here might just bump into another air particle. It actually won't bump into a wood particle. But some of the wood particles will start to take some of the kinetic energy away from me, and I will sense that as being a little bit cool. So maybe that takes a little kinetic energy, that bumps into this guy, and then so the kinetic energy does get transferred down. But it's going to be transferred down a lot slower than what would happen in the metal. Because one, I don't have as much surface contact between my hand and the wood because of these gaps. I also have air pockets. I have air pockets in the wood like this. And in general, the wood is less dense. So there's going to be less collisions, and it's going to take more time for that kinetic energy to be transferred away from my hand. In the metal, on the other hand, as soon as this atom bumps into this one, that's going to bump into that one, that's going to bump into that one, that's going to bump into that one, and that kinetic energy is going to be very quickly transferred down the metal. So it's going to be able to take more heat away from you, because this one's going to be this molecule right over here. It's going to get some kinetic energy from a molecule in my hand, but then it is going to bump into its neighbor and transfer that kinetic energy, and so it's going to lose its kinetic energy quite quickly, and so it's ready to be bumped into again by another molecule from my hand and take on more kinetic energy. So it's going to sap the heat away from me faster. So you have faster heat transfer than you have with the wood. And from your body's point of view, this heat being sapped away from you faster, even though the two surfaces are actually the same temperature, you perceive this, your body perceives this right over here as being, your body perceives that as being colder.